Okay, thanks. Good morning, everybody. I am Stefano Rodinò, a PhD student from University of Calabria, and today I will talk about the design of composite active material, and the main topic of this study is the evaluation of the interfacial strength between an SMA wire and a polymeric matrix. Here there is a short outline of the presentation, starting from the motivation and following through the introduction of the shape memory alloys. In the final steps, I will show also some material and experimental data and the implementation of a numerical model. And finally, I will show you also some prototypes that we have made and tested under aerodynamic load conditions. The first motivation is of this study is for shape morphing purpose. The shape morphing is a principle to the formal surface, and it consists in passing an SMA wire away from the neutral axis of the polymer of the section of the polymer, the composite, and then with a thermal actuation you can perform a sort of deflection. Multiple configurations are available for these technologies, and this project is made in collaboration with the Stellantis group, and the main aim is to apply this technology to multiple parts of the car, of a commercial car. When one are dealing with the design of active composite material, have to be phased out with the addition strength that play an important role in the load transfer between the polymeric matrix and the SMA wire. So the aim of this study is to evaluate the interfacial strength by sample out test, and also to develop a specific system to multiple apply cycles of actuation to the active composite to evaluate the fatigue life behavior. The active material of this study is the shape memory alloy that are basically a material able to recover strain and have two main functional properties that are the shape memory effect and the pseudoelasticity. The material is composed by two phases. That one is austenite, that is stable at high temperature and low level of stress, and another is the martensite, that is stable at low temperature and high level of stress. The main properties is the shape memory alloy, that is basically the properties of the capability of the material to recover a pre-strain that can be imposed during the cold phase under the martensite finish temperature, and then the material, when heated above the austenite finish temperature, will recover the fully pre-strain impressed in the cold phase. The material chosen in this study is an NiTi wire with a diameter of 0.3 from the Sgambitterra producer, and all the data was obtained by the datasheet of the material and also through some experimental tests made in our laboratory. There are two different experimental setups that we have made to evaluate the performance of the addition on the surface. One for thermomechanical fatigue purpose, and is composed by an aluminum frame, and the sample is passed between a load cell and a linear variable displacement transducer. There are also a set of calibrated weights that we use to perform different fatigue tests with different constant load conditions. The system is also composed by a programmable power supply and a data acquisition software. For the static pull-out purpose, there is in the first step the tensile test machine, obviously, and the test procedure is a displacement controlled test with a movement velocity of about 1 millimeter per minute. The sample is an epoxy resin cylinder with an height of 100 millimeter and an external diameter of 10 millimeter with an SMA wire of 0.3 millimeter embedded in itself. We have performed three different typology of tests. The type 1 is a pull-out test with a pure mechanical load on the manufactured sample. The type 2 is a pull-out test in which there is a combined mechanical and thermal load, both applied at the same time. And the final one is the pull-out test with a pure mechanical load, but compared with the type 1, there are first 1000 of thermal activation cycle. The chosen electrical inputs are a current level with a 1.12 ampere and an actuation time pulse for each cycle of 0.75 seconds. In this slide are shown some results for the type 1, type 2, and type 3 of tests, and one can make some important consideration. From the type 1 is the test that show the highest value of the average shear stress. The type 2 is the test that show the lowest value of the average test of the shear stress. And finally, the type 3, compared with the type 1, is showing only a slight reduction of the addition strength, also after 1,000 of actuation cycles. So in the design of this composite material, the temperature play a very important role on the addition strength. Another experimental test was carried out based on thermomechanical fatigue test with different load conditions from 200 megapascal to up to 300 of megapascal, and the specific specimen was actuated until the complete delamination of itself. And the results are plotted on a log-log graph, and that show the fatigue strength versus the actuation cycles until the run-out cycles of 5,000, and show a typical behavior of fatigue. Also, a numerical implementation was carried out in the COMPOSITES multi-physics environment with a 2D axial symmetric simulation, and the model used for describing the SMA nonlinear behavior of the NiTi wire is the Laguta's model that requires multiple parameters to be calibrated that can be obtained through some experimental tests. Also, in this simulation are considered some thermal aspects like volume change due to the increase of temperature, the temperature influence on the elastic properties, and also some phenomena of heat transfer that are present between the SMA wire and the polymeric resin block. So the polymeric resin block is not an isothermal domain. Some results are shown in this slide, particularly for the type 1 experimental test and type 3 of the experimental test. And the interesting thing is that both the tests show the same distribution of the shear stress along the interface between the SMA wire and the resin block. Also, some prototypes was designed. The solution 1 is to insert directly the SMA wire during the lamination process of the carbon fiber reinforced polymer, but this show very bad performance. In fact, some crack in the lamination occur during after some actuation cycle. So we switched to another solution that is solution 2, and is based on an assembly composed by a polycarbonate base plus a BS and 2 metal terminal and an high temperature silicon that cover all the wire. This solution compared with the solution 1 show lots of advantages like actuation response that is particularly fast. You can modify in real time the deflection. No damage on silicon matrix are encountered, and so the multi-layer composite is a structure able to return to completely flat configuration. This specimen was also tested under aerodynamic load condition and with a velocity of the flow of about 130 kilometers per hour. There are some conclusions that I want to talk about. That is the temperature for sure that play a very important role in the design of the active composite material, and also the choice of the SMA, the type of SMA material that sets the maximum temperature that you have to reach to fully activate the SMA material. And also another thing is that the fatigue life of the addition of the material decrease with the increasing of the mechanical load. Thanks for attention, and I leave here my contacts if you need some clarification.